In the previous module, we discussed the application of quantum transport phenomena and how some of the devices that we discussed so far in the previous modules are used for a technology called quantum electrical metrology. In this module, we will discuss the application of the quantum transport phenomenon and some of the devices for another application which is very fastly evolving as quantum information technology or qubit technology. So we will look into what are qubits and overview the current state of art of qubit technology using various quantum systems and focus on solid state qubits, and we will discuss the physics of superconducting qubits and also semiconducting qubits in one of the coming lectures. Okay. So before we discuss the solid state qubits, let's look at how the computing technology or the semiconductor technology has evolved over the years. And this graph is a little bit old, but you can get a feeling how fastly the density of devices on a processor has evolved. You can also see some of the other performing parameters such as the clock speed, power used has evolved over the years. So as you can see, the green one is the number of transistors that has gone up pretty fast. This is one version of the Moore's law. Okay. And if you look at the clock speed also had been going steadily until we hit something like a few gigahertz. Okay. So that is in 2000s and beyond. Then later you can see that the clock speed has actually tanked to a few gigahertz scale. Okay. This scale is in megahertz, so you can see 1000 megahertz is a gigahertz. This is plotted in megahertz. And if you look at what are the issues, one of the main thing is the clock speed is bandwidth limited by the resistance and the capacitance involved in the circuit. You can see that these are very densely packed, and as you increase the number of transistors, or as you increase the density, you will increase the capacitance and you also will increase the resistance. Both those will contribute, and which will effectively is providing a limit to the RC or the time constant. Resistance and the capacitance is going to give the time constant of the circuit inside, and beyond certain density you cannot go further in the clock speed, and the clock speed has been capped to few gigahertz, and that is still going on. Still you have like a few gigahertz of clock speed, but you overcome that limitation by increasing the number of cores. That is what you do now. You have more and more cores, CPUs with more and more number of cores. Okay. Now the issues here are the joule heating. You get a lot more power consumption because of the heating takes up a lot of your power, that you can see here in this picture. And this is a typical packaging, typical density of the components inside. You can see a lot of connecting lines, a lot of buses, a lot of It's an overview, okay, to give you a feel. And secondly, it's bandwidth limited. But more fundamentally, there is another issue, that is the quantum mechanical effects. That is the quantum confinement effects and the quantum tunneling effects also will come into picture. Those are not really, you cannot address those classically. Those are quantum mechanical effects. Those are inherent effects, which you need a different kind of approach to solve. Okay. Now, this slide is one of the first slides that we discussed during the start of this course. I'm not going to go over the full, slide here. I just want to point out some of the remaining topics, or some of the topics which was hanging around that time, which I just want to point out. This slide is also another version of Moore's law. You can see how the size has gone down over the years. Here is on the x-axis. Okay, we started with a large transistor, and now you have like transistor with a few nanometers in size. And post 2000, there are new technologies have come up. That is, the quantum dot devices have come up. Then superconductivity has been around for a while. Now you have the quantum dot qubit technology and superconducting qubit technology. Both of these evolved around similar time. And that is the topic of discussion for this module. And later, you can see that close to 2020, later part of the post 2010, you have multi-qubit systems have been demonstrated. And recently, a large number of qubits have been integrated, and a processor has been demonstrated by Google. Okay, that was a huge technological breakthrough. Okay. So starting from a single classical transistor to billions of classical transistor, now starting from a few qubit systems down to like now tensor qubit system has been demonstrated in the last 20 years. And this tremendous achievement, you can see, starting from 1950s to 2020, for 70 years. It's a huge technological revolution has happened, mostly because of the development, understanding and development of microfabrication and transport phenomena. And rest of this lecture and the next 1 or 2 lectures, we will concentrate our discussion on this qubit technology, that is both the quantum dot qubit technology and the superconducting qubit technology. This is just going to be an overview. This is not a full qubit lecture or anything, but just to give you highlights and give you a feeling that the topics that we addressed, learned the past few modules, how they are applied to this topic, this field. So, talking about the qubits, let us start with the classical bits. Those are basically the states of classical system. Consider this MOSFET as an example, and everything that we see in today's computer or today's semiconductor technology are in bits. Those are either zeros and ones, or we can say off state and on state. There are 2 states. Those are the classical states of the system. As far as a MOSFET is concerned, either it's an on state or it's an off state. Or it's a current is flowing through device, or the current is not flowing through device. In one case, it's a low current state, it's a high current state. Okay, those are classical states of the system. Which are classical states, 0 or 1. Those are bistable systems, but these states are classical states. The quantum mechanical counterpart for a bistable system can say they have 2 spin states, for example, spin up and spin down. or two states of any system. Okay, but those states are quantum mechanical states. Now, the drastic difference here is the moment you talk about quantum systems, you cannot basically escape the other fundamental property, that is quantum mechanical superposition. That means the moment you take any two states, that is 0 or 1, you can put these two, add these two states and get a third state, which is as good as any of the two starting states. In this picture here, what you are seeing is a block state representation, block sphere representation of the qubit state. You have 0 here, you have 1 here. You can add 0 and 1 with the coefficient, which is the weight factor or coefficient for this 0 and 1 state. And you can generate any other state. You can generate a number of states just using these zeros and 1, which is not something possible here. Okay. So you have a lot of states which you can represent using these zeros and 1s. And similarly, as you increase number of qubits, those number of possibilities also goes up enormously high. Okay. So that is a fundamentally different approach, or that is a fundamental difference between a classical bit and quantum. And of course, every other aspect of this computation also will change. You will have new algorithms. Those are quantum algorithms. Okay. So these few statements here are just to give you a feeling of how powerful this new idea is. A process which we can tell how powerful a computer is, or just to give a comparison between a classical computer and quantum computer. A 200 digit number can be prime factored by 170 CPU years, whereas a quantum computer, a 600 digit can be prime factored in 6 CPU days. Okay, and these computers can find answers to various things which are otherwise impossible for a quantum or for a classical computer. This can be quantum database search, simulation of various fundamental quantum process in chemistry and solid state physics, which requires a large or huge computational resource. So altogether, the approach of quantum computation is radically different from that of classical computer. And the very first, the difference is so fundamental that it actually starts from how you define the quantum bits. Okay. So these quantum bits are, in short, these are also called qubits. And how you define these qubits, that also you have a lot of options or a lot of approaches for a quantum computer. And we will overview that in this lecture. So the qubits are the states of a quantum computer, or the bits are the states of the classical computer. And we also discussed in the previous slide that generally these are two-level systems. So we have two state systems. In classical computer, it's an on and off state. The quantum computer, those are two states. Okay. So what we are looking for is a quantum two-level system to define our qubit. These are a few examples of quantum two-level systems. So a Bohr atom can consider the lowest two states, E0 and E1, the ground state and first excess states. You can say if the system is in the ground state, it is 0, and if the system is in the first excited state, it's 1. Okay, but these are quantum states. That's why I'm representing these as gates here. That's one example. And you can transfer the system between these two states, or you can put the system in the superposition state, okay, by appropriate mechanisms, such as you can transfer the system between these two states by using radiation in an atom, in a normal number atom, using radiation, which is equal to the frequency is equal to h bar omega equals to the energy difference between the two states. This one example of a two-level system. But there are other levels also here, which we have somehow make sure that the system stays between these two levels, in these two levels. So it's a subset or a subspace of the entire state vectors. Now, another example for a bistable system. There are many examples, okay? I'm just mentioning a few just to give you a feeling. An ammonia molecule, which actually can stay in between these two configurations. Okay. These are two torsional states where the three hydrogen atoms, and nitrogen is in this state or in other plane. Okay. If you consider the hydrogen atoms are in the plane, nitrogen can be on top or bottom. Okay. So, but these two are two different states with same energy. In this case, these are two states with two different energies, but here these two are two states with different energy, and they are orthogonal. Here also these are orthogonal. Okay. And you can also transfer this state from one to other by the application of radiation. Okay. You can have the system in this 0 state or 1 state. And you can also put in a superposition state. Another example is the spin state of a donor nucleus, say phosphorus 31 in silicon 28. You have one of the donor atom here. Okay, the spin state of this is another example. But now the question is, can any two-level system give you a qubit? There are a lot of opportunities. There are a lot of options. Like you can have n number of quantum mechanical systems, various kind of confinement, and you can somehow restrict the system to the two levels. And can they make a qubit, or can you make a quantum computer by using these systems? That is the natural question one would like to ask. But the answer is very interesting, and it's actually no. So you can make one qubit, but to make a quantum computer, you actually need to make sure that this system that you are hosting these qubits need to satisfy certain criteria, because those criteria are based on technology or how you realize the system in practice. Okay. So these criteria are put forth by DiVincenzo. Okay, these are called DiVincenzo criteria. These are criteria for the physical implementation of a quantum computer. Whatever is the qubit, how you make a quantum computer out of that qubit. So eventually, a quantum computer is an architecture. Like what I have shown here is a representation of a practical processor with various wires and running to it and out of it, taking signal in and out. Those are electrical signals. And this is when you look closely to one of those processors, you will see many number of buses, many number of devices, transistors inside connecting from between various points. Okay. It's a nanoscale construction, just like a real-world city construction. This is a aerial view of Barcelona, Spain. So you can see there are various roads, various buildings, various blocks that are connecting roads, connecting paths. Similarly, there is an architecture for a processor. Okay, so when you make a quantum computer, that processor also need to have some architecture. You cannot have few isolated qubits here and there, but you are talking about packing a large number of qubits in a systematic way. And we can address it, we can read the state of the system. Okay. Considering all these technological challenges or technological issues, there are few criteria. There are a few criteria put forth by Dimension. So first of all, you should be able to address these qubits individually. So if I want to read certain qubits, or if I want to tell that qubit to go from state 1 to state 2, I should be able to address it individually. Each of them I should be able to address it, which is important for initializing the qubit. So I should be able to initialize each qubit. I can put in everything is 1 or everything is 0, whatever the state I want. Okay. And I should be able to perform 1 and 2 qubit operations, rotations, operations. Okay. Those we will not go in detail. Okay. But those are fundamental requirements. And read out the final state of the quantum state. You have done your computation, whatever calculations or operations, and I should be able to read out the outcome in a single quantum measurement. These are quantum state, and I should be able to measure it using a single quantum measurement. This measurement also is going to affect your system. And there should be small decoherence rate. Okay, now we are talking about quantum mechanical system. So coherence, we are talking about wave functions. So the system, the wave function should not collapse or go to some other state, or undergo. There should be minimal decoherence effect, or that whatever the decoherence time scale should be much longer than the computation time. So you should be able to perform your computation much faster than the decoherence time. Okay, that is another fundamental requirement. So you have to consider, or you can consider only systems which obeys these guidelines. Okay. So based on that, we can tell there are not many systems or many candidates for the qubit construction, qubit technology. So some of the previous candidates, previous plural systems that we discussed cannot be used, because a normal atom is very hard. Okay. And this is also not scalable. That the term is scalability. So scalable means, can you make n number of identical molecules of ammonia, for example, and I can address it individually? Can I do that? It's very hard. You can demonstrate all these things in 1 or 2 molecules. But when you're talking about a quantum mechanical processor, the scalability is a huge issue. Same thing with this also. These are donor atoms inside silicon, and they are randomly placed. We are not going to place donors very orderedly. Like if I want, somebody is asking me, why don't you place like 1,000 atoms in a row? It's not possible practically. Okay, in a very structure, it's not possible. These are the issues of impurity, because these are there is a statistics to it, which there is an error over you place, and it is random, pretty much random. Okay, so there are addressability issues. There are scaling issues with most of the systems. So these are not really practical solutions to make quantum computer. Based on that, we have a few candidates, and that is what we will discuss now. So by looking at the DiVincenzo criteria, there are few system people have started exploring, and now they have zeroed down to 2 or 3. Okay, so ion traps. That means you can use optical or magnetic fields, or a combination of these. You can trap ions and use the hyperfine states or other quantum mechanical states, which you can transfer between those states by using electromagnetic fields, such as light pulses, lasers, and you can trap them in a very nice periodic way. Okay, using a combination of electrical magnetic fields. Okay, that is one technology which is now making a lot of progress. There are on-chip versions of these traps, like micro ion traps also. That is one approach. And similarly, you can use, instead of ions, you can use ultra cold atoms, and you can make periodic arrays of that. and use light pulses to something like optical lattice. You can trap using lasers these atoms and use the quantum state. Okay. Then another thing is you can use semiconductor impurity, but that is same as or similar to what we just discussed, the phosphorus donor impurity in silicon. But the advantage of these first three systems, which has very long coherence times, but because of scalability, the semiconductor impurities are not more a good choice, and there are not many reported progress in the systems. I would say the ion traps, the first three ion traps are the ones which are making a lot of progress now. Okay, but this third one I mentioned because it's a solid state system and quantum transport is a solid state phenomena, but that is not really now making much headway or progress. I would say the ion traps are pretty promising at this point. They are going in this first two ion traps have made a lot of progress. Okay. Now coming to solid state systems, there are superconducting circuits and there are semiconducting quantum dots. So superconducting circuits, they exploit the charge or flux degree of freedom in Josephson junction devices. Okay. This is an example of one of the superconducting circuit which has many qubits in that. This is technology what we are going to discuss after this slide. And this is scalable technology too. You can follow simple micro fabrication techniques which are perfected by the industry. Okay. And this another choice is the state of electrons in gated quantum dots. That means you have electrons in quantum dot, the spin states. You can trap electrons in quantum dots, which we have discussed, and you can use the spin states of those electrons to store and manipulate information. That also we will discuss in, if not in this lecture, in the next lecture. So those are the two solid state systems which are making a lot of progress and news nowadays.